This video is designed to introduce the mini projects that students will be completing throughout the semester. These will be completed outside of class, and that means we won't be spending much time in class for it. So I wanted to give some reinforcement and instruction to help you get started and to help you know what is expected of you. And those mini projects are pretty much one per week. To earn an A, a student needs to pass 9 mini projects. To earn a B, a student needs to pass 5 mini projects. And other than that, it's entirely optional for the course. But they're applied problems that should give you an opportunity to explore some more detailed uses of calculus than we'll be able to do during class. But also, I like them because I can require your best work. You're typing up these solutions, they're going to look neat, you're going to write in full sentences, you're going to show me your best. When we do a quiz, there's a lot of urgency to that. We've only got 5 or 10 minutes and you're rushed. With a mini project, we don't have that. To earn a pass on a mini project, you want to go to specifications page, and you'll want to read through the specifications for any part of the course, but in particular for mini projects, there are quite a big list of guidelines. So first of all, so take the time to read this. I'm not going to go over it all now, but to earn a pass, your work needs to be largely free of any errors. You need to actually show your thought process, and it needs to be communicated at a level that is appropriate for the standard audience for Math 181, your fellow classmates. You need to show supporting work. I don't want to see just an answer, a numeric answer. I need to see how you got there. And you need to make sure you're including units and any interpretation that the problem needs. Don't leave the work up to the reader. If you've done that, you've done it wrong. Think about how you would try to present something to your boss or a team of workers. Make sure it's neat and that it is showing the full thought process and understanding and communicating the right pieces to everyone. It says here that you've submitted via PDF files. That's no longer accurate. We're going to submit a URL in Canvas. Also show us how to get that URL. And I specifically mentioned graphical elements. Often you're going to be importing images, graphs, things, and they need to be properly labeled so that the context is there. And if you don't earn a pass the first time, you can earn revise and resubmit from me if you showed a good faith effort, and if you get close to passing, you get a revise and resubmit, in which case you go back and you try it again. Come see me if there are questions. But yeah, these mini projects are not punishment. They're an opportunity to practice what we're doing in class. We're using something called HackMD. So hackmd.io, and that's where we're going to type up all of our mini project solutions. It has some nice features. In particular, it can do fancy math typesetting, but it uses markdown format, which will allow us to do things in a very nice and pretty manner. To show you this editor here, right now we're viewing the preview. We can do a split screen that shows the editor and the preview, or we can just go to the editor menu where we type things here. So notice in the split screen, as I scroll up and down, we see the code and we see how it ended up pasting here. In order to get to the mini projects, you're going to click on the menu. I'm going to go, maybe first what I'm going to say is you're going to create a new note. Then you'll go to the menu, down to import, gist, and you're going to click on that, and it's going to ask you to paste in a URL. That URL is on this main project page. You'll just copy it, paste it in, and import it, and an assignment will load. So that takes us to mini project number 1. For mini project number 1, you're asked to do some things that are a little bit tricky. So the first problem is about a car and its stopping distance. So if it was traveling 10 miles per hour, it took 5 feet to stop. 20 miles per hour, 19 feet to stop. 30 miles per hour, 43 feet to stop, and so on. And we want to do some calculus involving this and maybe even make some predictions. And to do that, we're going to come up with a formula. That formula is not obvious. What type of curve would that even fit? So what you're going to do for this problem is you're going to go to desmos.com, open up the graphing calculator, and then we're going to make a table of data. So for example, the table you're going to do is the table from the problem, but I'm just going to make up a new one here. 0, 1, 2, 3, 4, and 5. And I'm just going to add some values here. It's like 4, 1, 0, 1, 4, 9. All right, and if we look at that, it looks like the shape of a parabola. So we're going to say, all right, I think it's probably a parabola. What does a parabola look like? It's y equals ax squared plus bx plus c. And if we knew what a, b, and c were, we'd be able to get a nice curve that fits there. But the cool thing is we can have Desmos find it for us. So we didn't cover this in class, but it's a feature that I'd love for you to know because it could show up in a lot of your science classes. All right, so up here, the variables were x1 and y1. So I'm going to call it y1 and x1. And I'm literally just typing the number 1 right after the variable, and it puts it down in the subscript. Or you could use an underscore character, and that gets you to a subscript. All right, but now it's not going to be equal. We need to fit it. And there's no approximation sign, but the next best thing is the tilde character that's up above the tab key on your keyboard. And that tells Desmos that it should try to fit the curve. Now there's a problem here. I've got x1 as a variable, but this one I didn't put an x1 in. Aha. Now we know that Desmos has fit the best possible curve. In this case, it's an exact fit because I just picked nice, pretty points. But if I move some of these points around like so, then it's no longer an exact fit. It just takes the parabola that is the best fit of all, and it tells us the value of A, B, and C. So I could type in my formula here, make a new equation. F of x equals, in place of A, 0.892857 x squared plus, and then B was negative 3.52143 x plus, and then C was 3.78571. All right, so, and then if I wanted to make predictions and say, all right, what's the correct point when x is 10? I could just plug in 10, and it's going to tell me what the point on the red curve is. And that would be our prediction for the y value when x is 10. Right, somewhere around 57.857. You're going to use this curve fitting feature to answer the questions here. So how does one go about actually answering those questions? Well, notice that the questions appear in these colored boxes, but we're going to type in between those boxes. So I'm going to go to my editor, and if I scroll down to the bottom of that box, which is the box is between these triple colons, that's what's causing the blue box. But all right, you see that I wrote I can type more, and then I wrote a formula here. So we can edit what this says, and it will show up in the preview. Now the tricky part is, how do we get math? And the answer is we stick it between dollar signs. So I can type x squared, and if it's between dollar signs, it will actually put that 2 up in the exponent. How would we get a more complicated thing like a fraction? Well, in that case, you're probably not going to learn how to do the LaTeX code. So here's what I would recommend. Go to Desmos and type it in there. So x plus 4 divided by 3x minus 2. So there's a fraction there. I'm going to copy and paste that code, in to those dollar signs there. And voila, there is the formula. If I put a double dollar sign, it will actually put it in display mode, so it's centered and a little bit larger. Or just so you know what it looks like without dollar signs, you're just seeing the actual code itself displayed. So you always want to make sure you put the dollar signs so it displays correctly. Are there other ways to get math input? Yes, but it would involve importing images or other shenanigans that are actually probably more complicated than this strategy. This will give you the prettiest output. So part B, the question in this blue box, is offset by this triple colon delimited region. So we could type an answer here, and that would give us more input. So I'm going to say that there are a lot of questions to answer here. You need to write things out in full sentences, do your best work, make it neat, easy to read. Try to show me that you own this material. And I haven't addressed the calculus portion of this, but that's going to be covered during class. All right, the second question involves a very similar solution method. In this case, I've drawn a 50 by 50 grid, but I've asked how many squares could be in there. That's a really hard question to answer because there are lots of sizes of squares. There's the little 1 by 1 squares, those are easy enough to count. We could just do 50 times 50, but there are 2 by 2 squares or 3 by 3 squares. So for example, a much smaller question would be, how many squares are there in a 3 by 3 grid? Well, there are 9 little squares. There are 4 squares that are 2 by 2, and then there's 1 square that's 3 by 3. So in this case, there would be a grand total of 9 plus 4 plus 1 is 14 different squares in a 3 by 3 grid. And the way we're going to answer this much harder question is by answering some smaller questions first. We're going to find, or make a function that will give the right answer to this question every time. So g of x gives the number of squares in an x by x grid. So just on your own, you're going to find g of 1, g of 2, g of 3 is 14, we saw, g of 4, and g of 5. So you're just going to brute force those. Once you have that, you have some data points. You'll have 5 points you can plot, and then once you enter those in, you're going to follow the instructions here. In this case, once you've entered it, you will have to use a cubic function to correctly fit the data. And once you've got that, it will give you a formula, and that formula will let you figure out how many squares there are in a 50 by 50 grid, or for that matter, in a 2000 by 2000 grid, any size grid. So that's one of the beautiful pieces of being able to find this formula. And none of that's actually calculus related. Only the very last part of this question is calculus related. You're going to estimate g prime of 4 and then interpret that value. What is its meaning? That first one is one of the more difficult of the mini projects, but it's doable. Make sure you come and ask me questions if you have questions. Please start this early. Don't wait until the last minute. That's one of the biggest mistakes a student can make. Good luck. All right, for mini project 2, there are also 2 problems. The first question is on population growth. We have a settlement that starts out with 1,000 people, and each year the population increases by 10%. So we're going to fill in the rest of the values in this table, just knowing that each year it's going to go up by 10%. Then we're going to find a formula for those points. Just like we did in mini project 1, we're going to use the curve fitting capabilities of Desmos to find a formula for the population. And in this case, I used y1 and x1, just as the default table values, but you have to use whatever you see in your table. It's also possible to find this formula just by reasoning it out if you know much about exponential growth, but that's not something we've covered in class or that I'm going to spend more time on here. And then there are several questions to answer that involve interpreting the values, estimating the values of derivatives, using central differences, and Then even a cool little fact that's related to the derivative formula for exponential functions in general to answer for this last one, where you're just going to plot two different functions and then figure out what the value of k is by wiggling a variable back and forth. The second question also involves curve fitting. You can see that I like this a lot. In this case, we are given the dosage of a drug based off of the weight of an individual in pounds. We're going to enter these table values into Desmos and fit a quadratic formula to it, or a quadratic equation, and figure out what our formula actually looks like to model the dosage for a given weight. And then we're going to answer some questions that are calculus based and make sure you're using units and that you are answering the exact question as it's written. Often students are answering related questions, but not the exact questions. To submit an assignment, make sure you go up to Publish, select Publish, and then copy the URL once it's been published. To submit an assignment, go up to this Publish link, select Publish, and then to share it, click on Copy, and then that new URL is the one that you will submit. That URL is the URL you'll submit to Canvas when you submit your assignment, and that will allow me to see your work. Mini Project 3 is a bit different. In this one, you're going to be creating a lesson where you teach someone else how to do one of the exam problem types, and you'll do that via a text message conversation. Now, usually text messages don't give you very good math formatting options, so we're going to do that here in HackMD. And to carry this out, you see here is a dialogue going back and forth between two people where I actually explain what the assignment is. So you're supposed to choose one of the sample exam problem types and write a tutorial explaining what concept is being tested and how you might solve it. And they talk back and forth about how to actually do that here. What you have to do to attain a pass, you're going to include an explanation of the type of problem that is being tested, why it's important, a demonstration problem that is different than any example we did in class, a full solution of your demonstration problem, and any study tips or hints that will help a student to succeed on a similar problem on the exam. So how detailed do you have to be? Well, it needs to be targeted at your classmates. Make it the lesson that you wish you had been given. If you had some magic tutor who could teach you how to do it, what would they say to you? And so in this case, the coding is a little bit different. You'll have to look at the left, but all of the pieces are there. You're literally going to be editing, and you'll replace this conversation with your own made-up conversation as you teach a lesson. Have fun with this. This is usually a fairly popular activity. Students do a good job, and as usual, ask me questions if you have them. Ask early and have a good time. All right, Mini Project 4 is about linear approximation and calculus. In class, we've seen this example of a potato placed in an oven, and we've seen how that temperature grows. Here, I'm asking you to find the local linearization, the tangent line, the linear approximation at a point, and then to use that to estimate. So we're going to interpolate or extrapolate. And for the most part, this is a fairly straightforward one. Please don't forget your units. Make sure you're answering the question that was asked. If you have any questions about what's going on, ask me, and please get started early. All right, in Mini Project 5, we're going to model the hours of daylight in a day throughout the year. And I've given you a formula that I want you to actually plot. Remember to follow the guidelines for plots. You've got to make sure you make it clear what your variables are, and the axes are labeled. You can use the wrench icon in Desmos to label the axes. And then you're going to start interpreting it. So according to that model, how many hours of daylight would there be on July 19th? Then you're actually going to go and look it up and see how close we predicted it by using a model. We're going to then compute a derivative, good old derivatives of trig functions. I will tell you this function looks like it's tricky to differentiate, but it's actually not so bad. It's just a linear function inside a cosine function, and the chain rule will give you a nice answer without too much difficulty. Don't make that one any harder than it is. All right, then you're going to use that derivative to answer a few questions, including how you would find the maximum length of a day, or the day that has the most daylight in the year. For the most part, we've got all the tools there. Students usually do all right on this one, but as usual, let me remind you about getting your units right. Read very carefully what you have written and make sure that it answers the question. Good luck. All right, mini project 6 is a teaching lesson where you are going to once again create a lesson, but you will be creating that lesson in Desmos. So you're going to go to teacher.desmos.com and you're going to create a lesson on one of the problem types from the exams. That lesson should include an explanation of the type of problem that's being tested, why it's important, a demonstration problem, some framework in which students can practice answering the question, and be sure to include any appropriate images or other resources that will be helpful. And at the end, you're going to want to make sure you include an activity summary that tells what will be accomplished and how it's accomplished. And also any study tips or hints that you want. Make it fun. Let me show you what this looks like. So if I click on this, teacher.desmos.com, you will either have to create an account, usually just log in with your Google account that you've been using all semester. I'm already logged in, and you can see if you go to custom, it lets you create activities. I've got literally hundreds of activities that I've made. Ooh, 381 at this point. You click on new activity. You'll give it some title that's appropriate to whatever your topic is. And then you're going to start building. You can add various components like a graph component, a note component, or a table component. You can add multiple choice questions. You could add videos, sketch components where students can draw things. You're able to preview your work at any point in time and see what it would look like for students. Try multiple components, see how they work. It's very easy to make a lesson like this very boring, so I'd recommend looking for ways to make it fun, but for the most part, you're going to have to dive in and try things and see how you can do it. I will point out, though, if you do a note component and click down here, you can get it into math mode, where it will allow you to enter things just like Desmos does. So make sure you format things so that they look pretty. For the most part, this is a fairly popular mini project as far as mini projects go. So I hope that you will have a good time. I'm not going to tell you how many screens to put up or try to micromanage you on this. Just make sure you follow those guidelines and that you include the details that were asked for in the original prompt. Good luck. All right, mini project 7 is all about the shape of a graph. This is a good mini project for students to do because there will be a corresponding exam problem of the exact same flavor. So this one's also a warm-up for the exam. In this case, I've given you a function, f of x, and then I just tell you what f prime of x and f double prime of x is so that you don't have to compute them on your own. But then you're going to put together all the details from section 3.1. You're going to have to do a first derivative test. You're going to have to find inflection points, intervals of concavity, intervals of increase and decrease. And on top of that, talk about the domain and the x and y intercept. And ultimately, you're going to plot a graph. And here I ask you to do something that sounds very hard at first, but I'm going to show you how to cheat. So in theory, you could just use the work you've done prior and get your answer. But I'm going to jump over to Desmos, and I'm just going to plot a function. So f of x equals x sine x. Okay, suppose this were the function that you were asked to plot. And if I wanted to plot this guy in different colors, depending on whether the function was increasing or decreasing, I can do y equals f of x, and it will plot it. And I can come over here, if I long press, or if I click on the gear icon up there, it will allow me to change the color. But I can also restrict it so that it only plots the parts where the function is increasing. So inside of those curly braces, I'll type f prime of x is greater than 0, and that's the parts of the curve that we're increasing. So pretty cool. I can even add another restrictions. What if I want only the part that's concave up? Type f double prime of x is greater than 0. And now it includes only the pieces that were concave up. I can copy that line, paste it a few more times here, and then I just have to make sure that my colors match whatever was asked. So make sure you read that carefully. But I'm going to start flipping some signs so that we get all of the possibilities. Let's see, oops. And now different parts of the curve get a different color just because the conditions here are met at different times. And that's something that is specifically asked for you in the last part of this mini project. Mini project 8 is about some applied optimization problems where I'm asking you to select 2 out of 3 problems and to solve them. I need a full write-up. I want to include the full thought process and any pictures that went in with that thought process. And that does mean you may need to draw something, scan it, and import it, which can be done in the editor here. So there's this button to import images. And you do have to keep the file type small, like less than 10 megabytes, or it won't let you. I'll warn you about that. But also, you can draw it up on whatever program you're using. So there are 3 problem types. One of them involves stringing a cable between 2 towers. One of them involves finding the point on a parabola that's closest to 3, 0. And another one involves finding the maximum possible area of a triangle that's under the curve. For each of these, make sure you include units. I guess that's just the first one that has units. But make sure you're writing out a full conclusion. Remember, on any story problem, you have to end with a sentence showing that you fully understand what your solution means. Good luck. All right, mini project 9 is a related rates project. Again, there are 3 questions, but you should select 2 of them to answer. Remember, each related rates problem has those 3 pieces: a formula, a statement of what we know, and a statement of what we want. Make sure you include those in your write-up. If you need to scan in an image, remember, you can import an image by clicking on the insert image here. As long as that image is less than 10 megabytes, you can import it. But yeah, be sure to include units in your answers, and of course, a sentence at the end showing that you know exactly what is going on. Pick any 2 out of those 3, answer them, and then publish and submit. Good luck. Mini project 10 is a video lesson. In this case, I'm asking you to create a lesson for your fellow classmates, but you're going to be filming a video. That video could be of any flavor you want. You could do a screencast, like this video. You could record you showing a tutoring session, or you could just have somebody hold a camera while you write on a piece of paper. There are lots of options. Common craft style video where you make little stick figures that move around on popsicle sticks. Yeah, have fun with this. Don't make it too complicated, because yeah, it is possible to make this terribly difficult. I do care about the quality of the video, although I do care more about the content of the video and your explanation and what it gets accomplished. I don't want these to be more than 5 minutes, 5-minute max. Aim for 3 or 4 minutes, and that's what I'm looking at. All right. So your video may not exceed 5 minutes. You're going to submit a URL to the video. So you have to upload it to YouTube and make sure that it's set to public, and then submit it in Canvas. And as before, you're picking one of the problem types that we're getting tested on this semester, and you're doing a demonstration problem, and it needs to be different than any other problem that we had done in class. Include any appropriate visuals or any study tips. Make it the lesson that you wish you had received. All right, mini project number 11 involves Riemann sums. I've given us this terribly ugly formula here, this function that we are trying to find the area under. We're going to estimate it using Riemann sums. I'm not asking you to do any plots. For some reason, students keep throwing plots into their solutions on this, but I'm asking you to find a Riemann sum using 3 rectangles, a midpoint estimate using 3 rectangles, a left Riemann sum with 9 rectangles, a right Riemann sum with 100, and a right Riemann sum with 1,000, and then eventually to come up with an expression that uses a limit to give the exact area under the curve. So how are we going to do that? Well, we're going to go to Desmos. Oops. In Desmos, if you click down here, you can get to a menu, or if you just type in sum, it will show up the sigma notation. So we could do from k equals 1 up to however many we want. So n might be 3. We know the formula for a right Riemann sum involves f of a plus k times delta x. I'm using capital D because delta x is not something Desmos will let me type, all times delta x. And when we figure out what f is, well, in this case, that was that big ugly formula. And delta x we know is b minus a all over n. We can plug those pieces in. So, for example, if we had the tangent function and it was 1 plus 2k all times 2. So this would actually add that up, and we could change n. So once we have this set up for a right Riemann sum, we can get all the right Riemann sums. So interestingly here, we see the numbers bouncing all over the place. That's because the tangent function is crazy discontinuous and it bounces all over the place. But also because this 2 shouldn't be 2, it should be changing as n increases. At any rate, using sigma notation, you're going to be able to answer those questions. You don't want to do it all by brute force. Make sure that you include a full answer, and I should show you how does one write this last one. I asked you to use a limit, and Desmos doesn't let you do limits. So I'm just going to, in $signs, \limit, subscript, and then n going to infinity. That right there will allow us to write an expression involving limits. And if I put a double $sign around it, it will even underset things correctly and stick it out there. So you're able to write an expression. Oops. Like so.